We are ready to restart. Do you hear me?
Yes.
Thank you. So we have seen the simplest of the case of stochastic optimization. In reality, it's not always as simple. Let me show another example where I assume that the load distribution is not uniform between two bounds, like I conveniently did, but where it is, for example, here, following a Gaussian distribution. So Gaussian distribution are very often taken for good or bad reasons, but they are very convenient, so they're very often taken. I assume here that the load L1, for example, is Gaussian with a mean L1 bar and some variance, V1 here. If I apply the same principle of minimizing a cost function that must by nature not depend on the disturbance, otherwise we don't know how to solve such a problem, I have to compute the expectation of the total cost. Now, assuming the cost is quadratic, varies faster than linearly, this is often not extremely realistic, but it's taken in some dimensioning studies to express the fact that some generators have costs that increase faster when the set points become larger. If you want to run the system at very, very large value, it costs more than proportionally. This is true for some fuel-based generators, for example. In general, we would have a convex function, which is probably not exactly a square. But let's keep the square to simplify things here. Then what is the total cost? Well, you remember that in our example, G1 and G disappears because G1 is this function of the set points and the disturbances here. And now the C1 is a C1 of this, which is gamma times this thing to the square. So if I develop all this, G2 and G3 become those quantities square with the gamma in front. And then I have to compute the expectation of this, minus G2 minus G3 plus L1 plus L2 plus L3. Here I did not put it in appendix in subscript because the notation would be heavy, but we must remember that when we talk of expectation here, we're thinking of the expectation where the random variable is the vector L1, L2, L3. So the question is now a probability 101 question. What is the expectation of minus a constant plus the sum of three Gaussian random variables here? Well, it depends on the assumption we're making on the random variables. Here, I'm implicitly assuming they are Gaussian and independent, and therefore the expectation of a square of a random variable is equal to the mean of this random variable to the square plus the variance. That's a standard formula of probability. Expectation of x squared is mu, where mu is the expectation of x, plus v, where v is the variance of x. So here the variable x is this, here. What is the mean of x? Well, it is minus g2 plus g3 plus the sum of the means. That's the same thing as we said before. But now we have the variance that also plays a role. If I assume L2, L1, L2, L3 are independent, which is often done, but not always. Sometimes we have a covariance matrix for the complete vector. Here I'm assuming they are independent. And if they're independent, the variance of the sum is the sum of the variances here. So it's V1 plus V2 plus V3. Therefore, this term here becomes the value to the square plus V1 plus V2 plus V3 plus etc. So when the cost is quadratic or in general convex, we see that the expected cost is equal to the cost of the expected value, that's all this term and this term, plus a term for the variance here. Here too, we pay for the uncertainty when the cost is convex, even in the expression of the average cost itself here, which adds some complexity. The second level of complexity is the constraints. Remember, in stochastic optimization, we always have to handle those two things, the cost function and the constraint here. Oops. Now the constraint, we cannot put deterministic bounds on this case here because the Gaussian random variable has infinite support here. But in practice, the loads are not infinite, so Gaussian distribution is just a model. The reality is probably a bit different, and we capture this by saying that with a large probability, For example, if we take a probability 95%, which is not very large, but that's one that's often taken, we know that the random variable, that is Gaussian, with probability 95% is between plus or minus 196 times the square root of the variance, the standard deviation. That's a standard, one of those magic numbers that we were all familiar with concerning Gaussian distribution. If we massage it, if we have three independent random variables, that means with probability 1 minus alpha cubed, because we can deviate independently for each of those. So with this probability here, which will be a bit more than 1, which will be, so the probability of failing will be a bit more than 5%. Then we are within those three bounds here. So the bound for L1, for example, is the mean value minus eta, this magic number, square root of the variance, plus or minus eta, square root of the variance here. When we do this, in fact, we pretend that the random thing are within certain bounds here, which means we take a probability, we take a risk with some probability, the constraint will not be satisfied. But there is no way to do other than that, in particular, if we want to have reasonable set points that are not too conservative. For example, if we take a probability, if we take epsilon is this value, 10 to the minus 4 here, then eta will be 4.15 here, and the alpha will be 3.3, 10 to the minus 5, which will be the probability of not taking of the chance, the probability that our constraints are not satisfied. So we take that kind of small probabilities that gives us eta, or we take a larger probability that gives us another eta. And at the end, we have, same as before, we have now bounds that are obtained as before, and then we solve it with the same techniques as we've seen in the simple example. So in summary, when we do stochastic optimization, we have a system state that depends on the control and the disturbance. We want to minimize the expectation of the cost subject to feasibility. The feasibility is expressed typically by system state, constraints on system state. And this has to be true, the feasibility, for all values of the disturbance with a high probability, which gives this formulation. Minimize over the control variable, the expectation over the disturbance of the costs, that depends both on the control variable and the disturbance. In theory, that's how we write it. We've seen two examples. The first one, when we have linear, everything is made linear. When we have quadratic costs, it already becomes a bit more complicated. And then we replace the chance constraints by some, we replace the constraints with some probability, become some deterministic constraint here. So at the end, we will have a formulation of this C bar of U, which, because here it depends only on U, such that for all D in some set here, which are the chance defined by the chance constraint, such an inequality is true. And if we are lucky, if we manage to have inequalities that are of the separable form, then we have seen how to solve it at the expense of separating U and D and solving additional optimization problems. For example, now if I do it correctly for my smart grid of 3 nodes here, I'm showing here the exact constraints. Now I do it correctly, which means I have the quantifier. For all L1, I have this. I took the very first case, I assume the L1s are uniform input in those bounds, so that, or at least that the expected cost is simply given by this formula here. And now I have to robustify, to remove the quantifier from all those constraints, which means remove the quantifier and the L1 for all the constraints here. To do this, we've seen that one way is to solve for one auxiliary optimization problem for each of the constraints where there is a quantifier. In this example, how many supplementary or auxiliary problems will I have to use? Will I have to solve? I close the poll in a few seconds. And the majority says A or C, but none of them are correct. The correct answer is 8. Because here I have to see, this framework says I have one inequality where I have both U and D. Here I have 1, 2, 3, 4, 5, 6, 7, 8. So we have to really account for all inequalities. And believe me, in any decent sized problem, there is immediately a very large number of inequalities that come. In this example here, it's 8. So you'll be able to exercise more in the lab, not in this lab, but in the following lab. Now let's see an alternative method to stochastic optimization, which is very, very close and is most of the time called robust optimization. It's an alternative in the sense that it's non-probabilistic. Probabilistic optimization is used when you can reasonably say something about the distribution of the uncertainty. We have seen that even with quadratic cases, very quickly it becomes very complicated. So sometimes, very often, we prefer to avoid this complication with this method of robust optimization. In the context of smart grid, if you have a very large grid, for example, if you are running Swiss grid, if you're a Swiss grid, you're running the transmission network of Switzerland, then you have a good forecast of the future because you pay a lot to get this and you're a large entity, and also your system is large. So by law of large numbers, forecasts are easier to get, not easier to get, but are more serious. And because you're a large entity, you also have more resources to invest into making forecasts. So if you have good forecasts with good distribution, you will do stochastic optimization, like we said before. If you run a small grid, like a microgrid of a building or something like we will do in the lab, probably your forecasts are not as accurate. So you don't rely too much on chance constraints because those bounds that you have are perhaps not very serious. So what you will do, what you can do instead, is use robust optimization. And you can also combine, as we will see, you can combine the two, as you will be able to easily see. So robust optimization assumes the same framework. We choose a control. Nature chooses some disturbance. The system state becomes the result of our control, which we choose first, and disturbance is chosen after the fact, and we pay a cost here. But here the only thing we assume about the disturbance is we know an uncertainty set, but we don't need a distribution. We don't need a distribution because in that case, the cost that we take is simply the worst case cost. So robust optimization means two things. First, the disturbance is assumed to be within a deterministic set. And second, we replace the average cost by the worst case cost here. This is why also it's called robust. Here, the robust means that whatever happens, since the cost is the worst case, we are certain to be well protected against what happens in the worst case. As I said, it's motivated by simplification, but it's also extreme. So a combination that we often find is that we will use deterministic bound for the disturbances, but instead of the worst case, we might take some approximation of the average case, a bit like we did in the previous example. But for the time being, if we are interested in the worst case, let's see how we can solve this here. Well, the only difficult thing is to write. So there is the complexities in the description. For this smart grid example, I have to minimize, as we saw, the two control variables are G2, G3, and then we take the worst case over all the L1, L2, L3, and here I'm assuming that L1, L2, L3 reside in these uncertainty intervals here. And then this is the cost that I have obtained, and now the cost has the uncertainty, L1, L2, L3, but I'm taking the max over the uncertainty. So because we take the max over the uncertainty, the output of the expression that's in the square bracket here does not depend on L1, L2, L3. Right? This is the result of an optimization problem where the variables are L1, L2, L3, that will return one value that depends on G2 and G3, but does not depend on L1, L2, L3. As expected, we want that the thing we optimize for does not depend on G2, G3. And the other constraints are the same as before. Here we have the constraints that must be satisfied for all value of the disturbance. So that's the same as before. The thing that has changed is we have the max here. Now, one of the reasons people often use this is that this is in fact very simple to handle. In this specific case, it's even trivially simple, but we'll see that in general, even we can always solve it here, because here, the question is, what is the max of this expression when L1, L2, L3 are in this bound? But this depends on L1, L2, L3 in a monotonic way. You see that there is a plus sign in front of L1, L2, L3. So we see that if L1 is larger, the value of that is larger, and same for L2 and L3. And since the constraints on L1, L2, L3 are independent, we have boxes for L1, L2, L3 where they vary independently, then the max is when L1 is as large as possible, L2 is as large as possible, and L3 is as large as possible, which means we take the upper bound of L1, L2, L3, and obviously that must be the max. I say obviously, you always be careful when someone says obviously, it just means sometimes it's too complicated to explain. So let me explain. If I pick L1, L2, L3 being those extreme values, I have a feasible value. So that's a feasible point. And for any other value of L1, L2, L3, the objective is less than this one, because L1 must be less than 1.1, L2 less than 1.1, and L3 less than 5.2. So the sum will be less. So manually, I can show that this value is a maximum because it's feasible and it's an upper bound to any possible value of any feasible point. So that's the optimum. So in this very simple and atypical case, I stress that's atypical. Most of the time, we'll not be able to compute it in this form. But here we can compute the max, and we found that the max is obtained when the sum of the loads gives 7.4, which gives my objective function. So the only thing that we have changed with respect to the previous time is that we have put an offset in the objective function, which in this specific case doesn't change much. The constraints, we have the same problem here. And we get rid of the quantifiers using the same techniques as before. In general, we are not in this simple case where the max can be computed explicitly. So we have something that's apparently intimidating because we cannot solve this for every u, right? When we had those constraints here, we could solve this for every j because j is a number, is the index of a constraint. In the example I gave before, we had 8 constraints. So we do 8 times, solve an optimization problem. But here, we need to solve this optimization problem for every value of d, or call it d prime here to make sure it's not the same as here. D prime is a continuous variable, so I cannot solve it for every d prime. So I need something smarter. It turns out that we have seen already the solution. We have seen last week that when I have an optimization function, I have to minimize a cost function, and the cost is a max of a number of functions. Then we saw that we could replace the max by an epsilon, and the constraint, that is epsilon, is larger than all the values of the terms of the max. Last week, we saw it when there is a finite number of maxes, of terms in the max. But that works even if we have an infinite number, like we have here, and the reasoning is exactly the same here, provided that its maximum exists. If the set is continuous, of course, we need to make sure that this problem is well posed. That means that there is indeed, it is bounded and closed so that there is a point that reaches this, which is typically the case for what we do. Therefore, we can replace this mean of this max by adding one variable for the max, mean epsilon, overall u and epsilon, where I add the constraint that epsilon must be larger than this, phi of u and d, or d prime. It's a dummy variable. I don't care about the name I give it. For all value of d, that satisfies the constraint that is here. So we can, at the cost of adding one single additional optimization variable, get rid of this max, and also, by the way, of this computation of expectation, etc. So this is why this is very often used. It is because it's very simple to solve practically. Of course, we have here to solve for this, but we have seen how to do that. For example, here, this gives the following problem. Minimum, as an alternative to what I showed before, we can minimize epsilon over G2, G3 epsilon. So we have 3 optimization variables instead of 2, subject to the constraint for all L1, etc. And I add the constraint that epsilon is larger than that for all values of L1, L2, and L3 here. And we have seen how to get rid of the quantifier. By the way, here are 2 tentative solutions to this problem where we have no quantifier. Which of these is a correct one, do you think, if any? I close the poll in a few seconds. Closing. The majority says A. A is correct, but B is also correct. So both formulations are in fact correct. Formulation B is the formulation we saw by doing a manual computation of the max. I computed the max, and in this very specific case, I could have a closed form, and that gives this formula. So that's the formulation we saw a minute ago. Formulation A is the formulation we obtain if we do 2 things. First, we remove the max by adding an epsilon, and then we get rid of the quantifier by computing explicitly the 8 plus 1, 9 solution to the optimization problems. Now, those 9 values are easy to compute because those are monotonic functions. And this gives those 8 formulation we had here, plus this 9th one here. So A is also correct. That is what we obtain if we use the systematic approach. So B is an ad hoc approach, A is the systematic one. This illustrates also the focus of this course and the practical problem we have when we do OPF, or optimization problem for controlling a smart grid in general. You see that we had to do some work to transform a problem. First, we had to decide how to write the problem. Here I put a max rather than an expectation. So I had first to do this. MATLAB will not do it for me. And second, I had to transform it into something that MATLAB can solve. And there are different ways, and the different ways lead to different formulation. Of course, they're all equivalent, hopefully, in the sense that if we do perfect infinite precision math, we will find the same solution. But some solutions might be a bit different. Here, for example, we have more variables. So the number of variables, the complexity might be different. So take-home message, it's important to be able to really understand well all those techniques of what I call problem transformation. Well, we have seen the easy cases. Now, in the rest of this lecture today, we will talk of a bit more sophisticated technique, but that's very, very often used in the context of smart grids and electricity markets and multi-energy optimization systems, which practically very often involves duality. We have seen duality last week. We have seen the dual of a linear program. We have seen also this morning some duality in another sense. We have seen that we may have optimization problems with quantifiers in the constraint. And we have seen that if I have a for all quantifier, that leads to adding auxiliary minimization problem. If I have there exists quantifier, I have seen that that leads to auxiliary problems that are maximization. So there is a duality between for all and there exists. One leads to max, the other to min. Just like the dual of a minimization optimization problem is a maximization problem. And this interplay between the two is used to solve some robust problems that are otherwise very difficult to solve here. Because duality will transform a max problem into a min problem, therefore will transform a for all quantifier into a there exists quantifier. And a there exists quantifier is easy to solve because we have seen also that if there is a there exists quantifier in the constraints, that's equivalent to simply adding more variables to the problem. That's exactly how the technique, that's the program of what we will see now. Now let's dive into it and see that in detail. Before that, we need to do a small recap of the duality of linear programs here, which is a very well-known topic. But again, this is a topic that is suffering from variance in description. So all textbooks on linear programs don't all use the same terminology. So to be consistent with what I said last week, I use the Boyd and Vanderberg standard form. So let's see, for example, this linear optimization problem that we've seen already last week, minimize x plus 2y over those inequalities on x and y here. So I use step one by putting it into the form here that Vanderberg's and Boyd and Vanderberg's use. Remember that this form means that you have to choose an objective function, a domain, and constraints. Here I choose as optimization function, of course, f0 given here, I have no choice. The domain, I choose to put those constraints into the domain rather than the explicit constraints. That's a choice. I could put them in the constraints, I would lead to a different derivation that at the end, of course, will lead to an equivalent problem, but that's a flexibility. And I use here this choice here. So I assume the variables are non-negative and I add those as constraints. To put them in the form, I have to have a negative inequality, which gives this here. There is no equality constraint. So there are only Lagrange multipliers that have these constraints of being non-negative. If you remember, the standard framework imposes this. And the Lagrangian is the objective function, x plus 2y, plus lambda 1, the first inequality constraint, plus lambda 2, the second inequality constraint. So what I'm doing here is trying to use the Boyd and Vanderberg's generic methods to find what is the dual of C1. So remember that once we have put that into the standard form, the next step is to replace the constraint problem by the unconstrained problem, where we've put the constraints into the objective, which is the Lagrangian. So the unconstrained problem, there is one instance of the problem for every value of the Lagrange multiplier. So u of lambda 1, lambda 2 is minimize this expression. Now this expression we minimize over x and y in the definition set of the initial objective function here. So we impose x and y to be non-negative here. And we have to solve to minimize this, which is now a linear function where lambda 1 and lambda 2 are positive here. So I have to minimize this, a function of x plus y plus a constant here. So if I massage this, I obtain ax plus by plus c here. And I impose x and y non-negative here because that's the choice I did here. Now that's a problem that we can easily reason about, right? If the coefficients a, for example, is negative, and I want to minimize this, since x is constrained to be positive, ax might be as large as possible in absolute value with a minus sign, so the minimum would be minus infinity. So if one of the two coefficients here is negative, this problem is unbounded here. Remember, the second step of the generic method consists in finding the definition function of the unconstrained problem, which is the sets of parameters, lambda 1, lambda 2, where this problem is bounded, where the minimum exists, right? It's not minus infinity. So here it's very simple. If A or B is negative, the problem is unbounded. If both are non-negative, positive or 0, then what is the minimum of this? Where I have to minimize ax plus by plus c, where x is positive, b is positive, and c is a constant. So the smallest value is obtained when x and y are 0, and the optimal value is c. So this problem is very simple to solve. It is either unbounded or it's bounded, which occurs when a and b are positive or 0, and then the optimal value is the constant c here. Therefore, the next step, which is to find the dual function. The dual function is defined when the problem is bounded, when the minimum is well posed, which corresponds to saying a and b are positive. Remember what a and b are, so those values. So that gives us constraint on lambda 1 and lambda 2, which are given here. And then the dual function, which is the minimum, which is equal to c, because the optimization function is c then. And when it is defined, we find that the value is exactly equal to c, which is 5 lambda 1 plus 8 lambda 2. Therefore, the dual problem consists in maximizing. Remember, the dual of a minimization problem is a maximization problem. The dual function, which is 5 lambda 1 plus 8 lambda 2, subject to these inequalities, which come from here, and subject from lambda 1, lambda 2, which comes from the generic framework. So bingo, we have found the dual, or one form of the dual of this problem, and we see that the dual of a linear optimization problem is a linear optimization problem. We see also that there's an interesting interplay of the coefficient. We see that the coefficients 5, 8, that were the inequalities here, they become coefficients of the objective functions. And in contrast, the coefficients of the objective functions, 1 and 2, becomes second terms in the inequalities of the constraints of the dual problem. So the dual exchanges the constraints with the coefficients here. In general, we can do that and obtain the following statement. Here I simply copied what you find on Wikipedia. So again, the difficulty here is not in doing what I've done here. We've seen that by a simple and systematic approach of the framework of Boy and van der Berg, I'm able to derive the dual of this. But of course, since this is always the same, you can do it once for all. And then you find those 6 general problems here. Why 6? Well, because the dual of the dual is the primal. So if I have an optimization problem, which is of this form, a linear objective with linear equalities, and the only inequalities are the optimization variable is non-negative, then I obtain the dual, which is this one. I said the dual from here to here, it works in both ways here. Now there are variants depending on whether we impose, you see the special role of y being less than or equal to 0. You see that those constraints, they can be treated as general constraints, or they can be treated separately. Of course, there are multiple boxes in which a problem falls, right? So this is the generic problem, for example, because I can always put the inequality y larger than or equal to 0 as a special case of this here. But by doing that, I will increase the sizes of my matrices, so we typically don't do it here. So take-home message, if you have to write the dual of a linear program, well, you go by inspection through this table here. For example, here, which one is the dual of this linear program here? I close the poll in a few seconds. And the majority says B, which is correct. Well, it's not obvious if you don't have the mappings under the eyes, but by looking at the mapping that I gave, which is the standard one that you find, for example, in Wikipedia, then you find immediately this. So you recognize here that the constraints 10, 8 are becoming objective function, and the objective function become constrained, whether we have larger than or less than or etc. Well, this is where you have to look at exactly the details in a reference sheet here. It's interesting also to see this is an illustration of the feasible set of the primal program. This is an illustration of the feasible set of the dual program. We see that the dual value is obtained for some values of the Lagrange multipliers, which here I call lambda and nu, which are positive here. So this tells us something. We know that if a Lagrange multiplier is positive for an inequalities, and here that's for both, then it means that at the optimum point, both of those inequalities are valid with equality, which we do see here. We see that this point here satisfies the two constraints with equality. Therefore, we find that the two optimal Lagrange multipliers are positive also. And we have seen that in reality, when we have a large number of constraints, most Lagrange multipliers will be zero, but that the non-zero ones give us the limiting resources. We talked about that when we discussed the locational marginal prices and shadow price interpretation of the Lagrange multipliers. So why did we do all this? Well, it is because with duality, not just with linear programs, but in general, we can solve robust problems. We'll do it in the case of linear programs, because in the case of linear programs, the mapping is completely systematic and algorithmic. So it can be done in a generic fashion, which is what we will do now. We have seen how to remove quantifiers in problem with separable constraints. Separable constraints mean we have constraints of the form, a term in U, the control variables, and a term in the disturbance variables here. But very often we find also joint terms here. So if things are linear in U and D, if there's a joint term, that means it can be put in this form. For example, for every constraint J, there is a matrix B that multiplies D on the left and U on the right here. So it's linear in U and linear in D, but globally it's not linear, it's bilinear, it's quadratic globally if you take both D and U. So of course it's not the most general case, but that goes already one step beyond what we saw before, and we'll see that's very useful for doing smart and subtle control forms that are still linear, but are completely tractable and much more powerful than the method we saw last hour here. So the problem is now, how can I systematically solve a problem of this kind here? So the issue is, how can I get rid of the constraint here for all D here? So let's see an example. Here I have, let's take a take-home example. I have to minimize U plus 2V, two control variables, and I have a disturbance, which is a single number between 6 and 7. Those are controls on U, constraints on U and V. And here I have constraints that involves the robust constraint that must be true for all value of D. And we have, for example, this term here that involves du and dv. So those are the quadratic terms in U and V here. So that can be put into this form by casting, using simply the matrix that has 2 columns and 1 row, the matrix 11, 12. If I multiply matrix 11, 12 by the vector uv on the left and d on the right, I obtain exactly this equality here. So this problem is parameterized by the dimensions here, j, the number of equalities, the sizes of the matrix bj, which are directly derived from the sizes of the disturbance d, and the control variable u here. So in this problem, I have all those matrices here that give me my optimization problem. Well, to solve it, let's use the method we saw before. The first method, the first step consists in saying, well, I have here a for all, so I can replace the for all by a maximization problem. So this constraint here, I put all the D on one side and all the U only on the other side. That gives me this. Right? I have something that is linear in D. Now remember that when I solve this, it's for a fixed U. I want to write this for all D here. So if I put it in this form, I found that this expression of U must be larger than this expression of D. U is fixed now, and it must be true for all D. Since it's true for all D, it's true for the max here. It's equivalent to saying that we have the max here. So I consider the auxiliary problem, which consists in maximizing this here. Now, the bad thing is that this auxiliary problem depends on the continuous variable U. So it's a bit nasty. And if we would be just there, we're stuck, but we'll see how we can get unstuck by using duality here. So here I have a problem that depends on U. Theoretically, at least, I can compute its optimal value. That also depends on U. I call it P star of U, index J, because there is one such J for every coordinate. Therefore, this constraint is equivalent to that being larger than or equal to Pj star of U. So at least in theory, I have done the first step of my program, which consists in removing the D and the quantifier from this constraint. But I have this problem, I have this unknown thing, which is P star J of U. So step 2, I will now zoom on this problem here. How do I compute P star J of U? Then I had to solve an auxiliary optimization problem, which is indexed by U in a linear way, and is a linear problem in the optimization variable D. So here U is a parameter, D is a variable. That's really the only difficult thing about this story, is always keeping in mind what is a parameter. Parameter means it's something that is not an optimization variable, something that is fixed within when I ask MATLAB to solve the problem. And then I will transform the max into a mean by using the dual. Why do I want to do that? Well, because I have an inequality of the form. This is larger than the max, that's equivalent to for all. If I can transform that into a mean, I will have this is larger than the mean, and this will be equivalent to there exists. And we've seen that the there exists are much nicer to handle. So how can we transform a max into a mean? Well, by duality. We know that for linear programs, strong duality holds. So the dual will give exactly the same optimal value. So if I consider the dual, now using the cheat sheet I explained 15 minutes ago, the dual of this is given by this generic form. I have a vector of Lagrange multiplier. I have one vector per inequality. So for every j, there is a vector lambda j, which itself has many coordinates here. And this, which has a parameter u, right? But we've seen that when we have duality, the parameter that was in the objective function gets into the constraint, and the objective function comes from the constraint here. So we will have this optimization variable problem with new variables, the dual variables of this, with an objective that doesn't depend on u and constraint that depend on u. And we know, because strong duality holds, that this optimal value is the same. The optimal minimum here is the same as the max of this problem here. So what I've done is I've replaced this max, the constraint, by the max in the constraint. I'm just repeating what I did a minute ago. Then I said that the P star is simply a mean. Therefore, the constraint can be replaced by P star, which I write as the mean here. The mean of this is larger than this way. And then what I announced just a minute ago, we can apply. We can see that this is saying that u is larger than or equal to a mean. And we see that being larger than or equal to a mean is the same as there exists a value of the vector of Lagrange multipliers such that this is larger than that. which I write here, there exists a value that satisfies all those constraints here, such that this is larger than that. But now bingo is finished. I have replaced the constraint, the embarrassing constraint here by those here. So you see, I've replaced the for all into a there exists here. Now, once I have a there exists, I don't care anymore about the form of this here, because I know from a slide we saw an hour ago that there exists is equivalent to adding the variables to the optimization problem. So this problem is equivalent to minimizing the phi of the control variables, plus I add a vector of dual variables for every constraint, so that may make a lot, but I have now replaced the constraint with qualifier by a standard constraint. So I have a linear problem, which is much larger, but does not have any quantifier, and if it's not too large, can easily be solved.